It's week 2 of Come For Your Life. To make things more interesting, Jam and I are going to do a t-shirt giveaway.
To enter, go to Apple Podcasts or iTunes and write us a review and rate us, and we will announce the winners on August 15th.
Woo! Free t-shirt.
All right, let's do it. Good luck.
Hey, I'm Melissa.
And I'm Jam.
I'm a chemist.
And I'm not.
And this is Chemistry for Your Life.
A podcast teaching you about the chemistry of everyday life.
Jam, how are you doing this week?
I'm pretty good. It's been a little bit since we've recorded. Might not feel that way to the listener, but we haven't recorded in like 2 weeks.
Yeah. What did you do in those 2 weeks?
I went to Indiana. My wife is from there. All her family's there. And a lot of her friends still. She's got some good friendships there as well. So we went and had sort of a like marathon visit of like trying to get time to hang out with like 10 different people.
Yikes, that sounds like a lot.
It's actually, I guess it's kind of more than that because all of her siblings are married and have kids. So then it's like, it starts getting pretty exponential at that point.
Yeah. Yeah, I can't imagine trying to come back, if I left Dallas, trying to come back and see all the people I would want to see.
Seriously.
I'd have to be here for like a month.
Yeah, she doesn't get to see everybody. It's like she has to make a list of like, okay, I'm back and this is the many days that I'm here. Who are the people that I definitely have to see? So like people unfortunately get left off, but just because there's constraints. So
Now, did you see friend of the podcast, Becca Meck?
we actually did not this time. It was a bummer. We tried to, but it didn't work out. So
I don't know if she technically counts as a friend of the podcast, but she was hyped about it when she came here from Indiana.
I like that title, friend of the podcast. So what about you? What do you do?
Not a whole lot. I just worked and lived my life. But when this happened, I was so excited to tell you about it.
Okay.
So I've been ice skating. I've been taking ice skating lessons because I was born in the wrong state and I shouldn't be in Texas. I should be like from Michigan or Canada. Oh. And I love ice and hockey and all things not hot. So this is really not the place for me.
Oh, interesting.
Yeah, it is interesting.
And your parents are at fault, or?
Yeah, they actually are pretty sad and heartbroken that I denied Texas as my home. But so I've been taking ice skating lessons, and there's an adult class that I take with some adults, but there's also some kids, and I like kids. I think they're fun to talk to because they just don't take life seriously at all. And I got invited to play their game of tag, and I got schooled by these 6-year-olds. One in particular, I've played with her before, and she beats me every time, but we were in a smaller space this time. And so I was able to hang a little bit, but then finally I was like, okay, I need to work on my lesson. And then they literally came over and taught me things that I was doing wrong when I was skating. Yeah, they were so good.
That's incredible.
It was so fun. They're all probably like 10 or younger.
Yeah. Dude, that's crazy though, because it's like they learn stuff. I guess there's like similar things where kids can learn languages easier, but also there's a lot of things physically that I think that like kids can learn better because they, I don't know, don't have as much like bad habits about their muscles and stuff.
Yeah, they haven't spent like 28 years messing up their body. They're just like 6.
Yeah.
And most of that was just them growing to be the size that they are. So
Yeah,
and they start learning like when they're 3 or 4.
Yeah.
There was a little 2-year-old on the ice last week.
Oh my gosh.
It's so cute.
That kind of scares me, but I guess they don't have very far to fall. So it's
and they all wear helmets, and a lot of them wear like these big hockey pads, and it's so cute because they fall and they just like get back up and keep going. There's a really cute YouTube video. This is the last thing I'll say. Okay. There's a really cute YouTube video that I think it's Coach Jeremy post where he mic'd up his child at hockey practice, and it is precious. It is so funny, and that is a very good representation of what I experience on a weekly basis. Except these 6-year-olds, they're like really, really good.
Yeah.
But you also get to see these little kids being crazy. It's so fun.
That is fun. Dang.
Yeah. So that was my exciting thing. I was like, ooh, I can't wait to share this.
So what everyday life chemistry thing am I going to try to learn today?
Okay. So this is inspired by a roommate, an old roommate of mine, not a current roommate, who we were in the kitchen and we were just talking. And I have a habit of being in the kitchen and pontificating on about science. And somehow we got on the topic of margarine versus butter. So she didn't know the difference. Do you know what margarine is?
I've heard that margarine's like fake butter, but I don't know anything else other than that. Like people just use it as, I don't know. I mean, like I think we grew up knowing like the butter replacements that are like, I don't remember if, I can't believe it's not butter, it's margarine or not, but there's,
it's not butter, so it's something.
But that's all I know. I don't think I know anything else on the like, other than like the title level. Just not butter and butter. I think that's all I've got.
So that's pretty much she did. I don't think she even realized that the margarine was not butter, but maybe she did. No, I'm not sure. That's why I'm not calling her out by name specifically.
Yeah.
And actually, this was the moment I was like, I should do a podcast about this. Yeah. So this is kind of a special topic.
Okay.
So big shout out to her. You know who you are. Okay. So butter comes from dairy.
Yes.
It's a product of cow's milk. Margarine, not from dairy.
Uh-oh.
Not a product of cow's milk.
Oh, no.
Do you have any guesses about what it could be?
Aren't some, like, butter replacements just, like, vegetable oil or some sort of oil?
Mm-hmm.
Uh-oh.
That's exactly right.
So it's not even from a cow. Man.
So it's oil that's been forced to be a solid at room temperature.
Forced to be?
Mm-hmm.
Uh-oh.
They, like, trick it into being a solid at room temperature.
Dang, that's a nice cliffhanger right there. It's forced into it.
It's like, forced into it by this is what's so nice about being a scientist is you can manipulate molecules and atoms to make them do what you want. If that doesn't seem like a superpower, I don't know what does.
Yeah, that does seem like it.
So they can change the way that the molecules are arranged to make it be a solid at room temperature.
Yeah, because if you look at butter and margarine, like a stick of both of them, which I think you can get sticks of margarine, I don't recall them having like a crazy different look, which is probably on purpose. But interesting.
Okay, here's some questions for you to be thinking about.
Okay.
1, what makes oil a liquid normally?
Okay.
Like, why is oil a liquid versus a solid? And 2, how can you turn it into a solid?
Yes, those are questions I do now have.
Okay, so those are the questions we're going to be thinking about.
Okay.
We're also going to talk about saturated fats, and we're going to talk about unsaturated fats, and we're going to talk about hydrogenated oil and trans fats, and we're just basically going to get like down and dirty into margarine chemistry.
Okay, deal. Let's do it.
Okay, so for fat molecules that contain chains of long single bonds, so usually it's a long chain of carbons attached to each other.
Okay.
And each of those carbons actually usually has 2 other bonds, 2 hydrogens. Carbon is happiest when it's bonded with 4 bonds.
Okay.
So if you have a long chain of carbons bonded to each other, not branched, just a long line of carbons, it makes a shape that's sort of like a chevron shape. Do you know chevron, that pattern that got really big in like 2012?
Yeah, like it's kind of like 2 of the sides of a triangle, I guess, like a V or like a...
Like up, down, up, down, up, down.
Oh, okay. Repeating.
That's the chevron pattern.
Okay.
So girls made dresses out of it a lot. It's like a zigzag, like a long chain
Got
of
it. Okay, zigzag. Got it.
V's that are opposite. Yeah. Okay, so, and for those of you listening at home, if you're like, I don't still know what chevron is, then just Google chevron and you'll see it. Or Google hydrocarbon chains and you'll see it.
Maybe chevron pattern, because chevron's also like the gas station.
Oh, yeah. Chevron pattern, not Chevron, the gas station. Okay, so it'll make that nice chevron pattern. And because of that nice up and down at a consistent pace, those molecules can stack nicely on top of each other.
Oh, yeah.
Okay, so if they can stack nicely on top of each other, these long carbon chains with single bonds and fats, then they're going to mostly be solid at room temperature.
Okay.
So if your fat molecule contains a long chain of only single bonds, not a lot of double bonds, it'll probably be solid or semi-solid at room temperature.
Interesting. So it's because they fit together, it makes it solid.
Yeah, like it can have a more crystalline structure almost. It's not perfectly crystalline or it wouldn't have that softness, but usually things that can form nice, rigid, repeating structures are going to be more solid. Like crystals, salts have these nice, repeating structures.
Got it. Man, that's crazy.
Yeah. So, and that, it's a little bit more complicated than that, but that's probably the best explanation we can give with the time that we have. Okay, so for vegetable oil, its fat molecules, instead of having those long single chains, it has double bonds in it.
Okay. So what do those look like in terms of pattern?
Great question. They mess up the pattern. So they, instead of having that nice repeating up and down, they basically put little kinks in it. So imagine like chevron, up, down, straight line, up, down, straight line, a different direction.
Yeah.
So it just kind of messes up that nice stackability from that pattern. And so then they're less solid at room temperature because they can't nestle in nicely. They basically just take up more space and tend to be in the liquid form. Does that make sense?
Yes, it does. Yeah. Because they can't fit together. There's no I guess they sort of could, but wouldn't be consistent enough that it would be not at all even close to crystalline at that point.
Right.
Okay. Got it.
Okay. So if you want to take an oil that's a liquid and turn it into a solid, all you have to do is delete the double bonds and get it back to that nice chevron pattern, or delete enough of them to make it solid enough.
That's interesting. But how could one delete bonds? Like that sounds like it's more complicated than just pressing delete on your keyboard.
Would that you could only just press delete and the bonds go away. But it feels a little bit like that when you're writing it on paper, that it is just like a quick delete. But I think in real life, it's not that easy.
Yeah.
Okay, so this gets into a little bit of a more complicated part, and this is the more sciencey discussion behind how we go from a liquid to a solid at room temperature. So we talked about how basically the liquids have the double bonds that mess up the nice stackability.
Yeah.
And the solids have no double bonds, so they're nice and stackable for fat molecules. That's generally the trend.
Okay.
So we're going to delete those double bonds in the fat molecules to go from a liquid to a solid to make margarine.
Okay.
Okay.
And that kind of explains too,
No, that's great.
Just the fact that whenever you put grease from something you've cooked or whatever into something to let it cool after you've cooked and then you can throw it away or whatever, that as it gets close to room temperature, then it solidifies. I've always just thought that was more about heat than anything else, but I didn't think about the fact that it might just be like already how the molecules want to fit together when they're at room temperature.
Actually, that is what you're describing is what heat does. So heat will put energy in to make them move around, so they'll sort of not be interacting with each other as much, and so they'll spread further apart. And then as it cools down, they can form that nice stacked structure better. So it is about heat, but it's also about the way the molecules are formed.
Right.
Which is why vegetable oil doesn't do that, because it can't stack as nicely.
Yeah.
Molecularly.
Interesting.
So that's why technically you're not supposed to put like bacon fat down your sink because it'll solid up.
Yeah.
But it's okay to do that with vegetable oil theoretically because it'll keep going down your sink because it never becomes a solid.
Right. Also, how did they squeeze all the oil out of these vegetables?
I don't know that part.
Okay, right.
That is a great question. We should ask like how stuff works that.
Yeah.
Maybe they already have an episode on that, I bet.
Maybe they do. Yeah, they probably do. All right.
Okay, so I mentioned before that a carbon is bonded to 4 things.
Yeah.
And it's happiest that way. So that we're getting a little more into the nitty gritty of the science. So hang with me here so that we can explain how to delete double bonds.
Okay.
So
I think I remember that because carbon has the number 4 like on the periodic table, right?
Yes. Yeah. So it already has 4 electrons and it wants 4 more.
Yeah.
So 2 electrons will bond together and then 2 atoms share.
Kind of like we talked about with soap.
Yes.
Okay. So carbon, we weren't talking about carbon then, but carbon wants 4.
Yes, carbon wants 4. So, and that's all about valence electrons and stuff. So carbon wants to be bonded to 4 things. And so in these long carbon chains where it's a carbon bonded to a carbon, bonded to a carbon, bonded to a carbon, usually what that just pick a carbon, any carbon, as long as it's not the one at the very end of the chain, is bonded to 2 other carbons, 1 on each side, and usually 2 hydrogens to sort of fill in those last 2 bonds that it wants.
Okay.
So its 4 things are usually made up of 2 carbons and 2 hydrogens. When it's bonded to those 4 things, it takes a consistent shape.
Okay.
Have you ever watched Stranger Things?
Oh, yeah.
Stranger Things season 1?
Yes.
You know when Nancy is sitting on her bed studying with Steve?
Yes.
He asks her what shape they take. Do you remember?
Yeah, it's been a while though. I saw season 1 back when it first came out, so I was like 2017, I think, 2016.
I saw season 1 like a month ago.
Oh, okay.
So I saw season 1 for the first time, and they said this, and I was like, oh my gosh, that's a real answer. The shape is tetrahedron. So now you can go back and watch, what is that, the first or second episode, and see them studying, and when they say tetrahedron, you can be like, yes.
But what does that mean?
It basically means it's the 4 bonds are pointed to like the corners of a pyramid.
Okay.
So instead of it being like 4 flat, like 90-degree angles, each bond wants to be as far as apart from the other bonds as physically possible. And the shape that ends up getting them is a tetrahedron.
Okay.
So it's kind of 2 pointing up at a V and then 2 pointing down at a V at a perpendicular angle. It's kind of hard to visualize, but it doesn't matter a ton. Just know that it consistently takes that same shape. And when you line them up in a row, you get that nice repetitive up and down pattern that makes the chevron shape.
Okay, got it.
Okay. So when there's a double bond, so instead of the carbon being bonded to 4 things, it's bonded to 3 things. One of them twice. 2 bonds to 1 carbon, 1 bond to another, and usually just 1 hydrogen. So we've gotten rid of one of the hydrogens and formed a double bond with a carbon. The shape it takes instead is a flat triangle shape.
Okay.
120 degrees apart. You hanging with me?
Yeah.
Can you say that back to me just so I know that you got it?
So, just the previous one?
Both of them.
Okay, the first bond, which is single, makes it tetrahedron shape, which, because of the way it has like kind of a polygonal shape on the top and the bottom, it creates a chevron when they're next to each other.
Yes.
But a double bond, because it's a double bond, makes a triangle instead of making like a polygonal thing, which means that like, now I'm thinking if I tried to stack that, I couldn't just stack a triangle on top of a triangle.
Yeah.
Yeah, is that right?
Yeah, that's a pretty good understanding. It's hard to explain without having visual cues. So that's a pretty good understanding. So that is the whole problem. That's what causes the kinks in the nice chain. So when you get that double bond, it doesn't stack anymore because it makes the triangle shape instead of the tetrahedron shape.
Got it.
Okay, so that is a really good explanation. So to delete the double bond, the trick is to get it back into that tetrahedron shape.
Okay.
So we would, instead of having 2 carbons bonded to each other twice, to break that bond, you send in a hydrogen to form another bond with carbon. If that happens, the carbon will break its double bond, and there'll just be a single bond between the 2 carbons.
Got it. So if there's like available hydrogen and you can somehow just like get enough in there, it could just happen?
So in organic chemistry, in your textbooks, the thing you'll see most often is hydrogen, H2, with a metal catalyst like platinum, palladium, whatever.
A catalyst is...
Oh, that's a good question. A catalyst is something that facilitates a reaction.
Okay.
It's usually not used up in the reaction, so it's regenerated. But it basically just helps the reaction happen without being an actual part of the starting material or finishing material.
Okay.
So you basically put hydrogen gas, some kind of metal catalyst to help this happen, and that hydrogen gas will bond to each of the carbons and break the double bond.
Got it.
That's called hydrogenation.
Oh, because of the hydrogen.
Because of the hydrogen.
Because I've heard like the commercials, I think, where it's like, hydrogenated fats or whatever. And it's like trying to use those words to sound really smart. And also, I think they're trying to say that it's bad. So,
well, I don't think it's inherently bad. There's a lot of things in food world that are labeled bad or good that I'm slower to label.
Yeah.
Okay, so that's called hydrogenation.
Okay.
The double bond carbons, the fats with double bonds in them, they're not fully saturated with all the hydrogens they could possibly be bound to.
Okay.
Those are called unsaturated fats.
Okay.
The ones that are fully single bonds that have all the hydrogens that they could possibly bound to, those are called saturated fats.
Okay.
So you've probably heard all those terms in food commercials. Hydrogenation, saturated fats, unsaturated fats.
Yes, I have. Yeah.
We use hydrogenation to take a unsaturated fat and make it a saturated fat.
Got it.
All margarine is vegetable oil that's been hydrogenated to lose some of its double bonds so that it's more solid at room temperature.
And do they also like add salt to it to make it a little bit like salted butter?
Maybe. I don't know.
Because like there's times where I feel like the average person, and I'm kind of the average person in a lot of ways, wouldn't be able to tell just by taste if I didn't see anything else and just like took a bite of a piece of bread with it on there. I'm not sure that I would know.
Yeah, I should say on a food industry level, I don't know what else they add to it to make it taste like butter, but what the basics of it is hydrogenated oil.
Got it. Yeah.
So there's a lot of stuff I don't know. I don't know for sure what catalysts they use in the food industry. I don't know what else they do to it to make it taste more like butter or less like butter. But when we're talking about hydrogenated oil and unsaturated fats, that's what we're talking about.
Okay.
You got it?
I think so. Yeah.
Okay, so this is just a little teaser because we're not going to talk about this yet.
Okay.
But bad things can also happen when you hydrogenate unsaturated fats.
When we're messing with nature, something can go wrong.
When you're messing with nature, something can go wrong. And we're going to talk about that next week.
Okay.
That's the formation of trans fats.
Oh, no.
Oh, no.
I've definitely heard of those, and those definitely sound bad.
You've definitely heard of those. So that's just a little teaser.
Okay.
It's too much to put all in one episode because we don't want to talk everyone's ear off for an hour and a half.
Exactly.
But hand in hand with hydrogenated oils comes trans fats.
Interesting.
Okay, so you know everything that you need to know. Now I want you to explain to me what margarine is.
Yes, the part of the show where I have to try to prove that I was listening.
Where you prove that you're listening and that you're a good student.
Okay, so...
And I just drink my coffee.
Okay. Man, I like drinking coffee too, but I guess I'll take a break. Okay, so butter is the real deal. And part of what makes it in its butter state, and it's like solid, is the fact the way that the molecules fit together at room temperature in that chevron shape. And so that is the simplest way to know why it is like that.
Yes.
And oil, vegetable oil, isn't, because it has a shape that does not fit together like that. It doesn't have that nice click togetherness. And the way that the different molecules bond together can be changed in oil to make it fit together better so that it could become a solid at room temperature.
Yes.
And the way they figured out to do that was because of the way that the carbons are double bonded, if they can get some hydrogen in there, then those other carbons that are part of the double bond will bond to the hydrogen instead, which would make the nice structure of the single, and then they fit together nicely. So what you guys in your science labs did is you got some sort of metal because you need some sort of help, and you squeezed a bunch of hydrogen in there, and then the oil was like, okay, and the oil was like becoming more fit together, and
yes,
and that's how it can be a solid at room temperature.
That is exactly right.
It's also kind of fun to use layman's terms and like try to make it sound like a normal conversation anyone would have at like a coffee shop.
Yeah, I was just thinking about how I would maybe be crucified if I ever use language like this in a real science setting. But I think those kinds of layman's terms are incredibly helpful to understanding science a little bit more. Yeah. Use what you already understand to build connections with what you don't understand yet.
Especially because then I could refer to it in my everyday life without having to like completely change my vernacular.
Right.
Like it wouldn't be applicable to me if I was like, okay, not only do you have to figure out how this works and talk about it, but also you have to start using language you'd never use. Like,
right. Exactly. So now you can go tell your lovely wife, Emily, when you're making toast.
Yeah.
Hey, I know why this is solid instead of liquid, and I know what it's made of.
And I know that she will really want to hear how and why.
Listen, you'd be surprised. When my roommate and I had this conversation, she was like, oh, like really genuinely interested in what she was eating.
Yeah.
So you might be surprised. I mean, you might not be surprised, but people might be surprised at who finds this interesting.
That's true.
Great. You did a good job. What did you enjoy most about your learning experience today?
I guess it's that simple. Like, I know it's not like we simplified it a lot and you simplified it a lot for a non-scientist like me, but just hearing again, kind of like with the soap situation, that it was actually a pretty simple change that was made that changed a lot of things.
Yeah.
Like you just go on that molecular level and it can change how it looks and how it is useful to an average user like me. So it's like, just, I don't know, it's kind of weird to think that it could be that simple.
Yeah.
But probably a lot of these things are, which is just, yeah.
Yeah, I think that's true. I think that science gets a bad rap because it seems so intimidating.
Yeah.
But a lot of it is, it's just been presented in an intimidating way, but it can be understandable and interesting and fun.
Yeah.
And now you can go tell people, like, I know more than you know about butter.
And I think not already understanding something, if that's the case for anybody, then I think most of the time when we're in that situation, we assume that the thing that we don't understand is actually more complicated than it really is. Sometimes that could be true, but I think many times we just assume it because we don't understand it yet.
Yeah.
And so it's kind of weird to be like, okay, I didn't understand this, but it's always been that simple to wrap my head around the kind of surface level explanation like that.
Yeah, that's how I feel about computers. They seem really scary and intense, but I don't think that they probably would be if I understood them a little bit more.
Right. And now me and the listeners hopefully understand margarine.
Yeah. Thanks for coming to listen and learn today.
Thanks for being able to teach all of us.
It's quite literally my pleasure. I love it.
And I'm ready to hear about the dark side of this whole deal next week.
Oh, yes. Come over to the dark side.
Melissa and I have a lot of ideas for chemistry of everyday life topics, but we want to hear from you. So you can reach out to us at Gmail or on Twitter or Instagram or Facebook at Chem for Your Life. That is Chem, FOR, Your Life, at any of those social media things or on Gmail.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and we'd like to give a special thanks to Autumn Kiwasong, who reviewed this episode.